All right, so continuing on with section 14.3, polarization of atoms. So we know that a charged object, so let's say it's a positively charged object, attracts a negatively charged object. However, if you charge something like a piece of tape, you'll see charged objects can be attracted to seemingly everything, including uncharged matter. You can test this out by rubbing your hair with a balloon and then seeing if your roommate's hair, which is uncharged, is attracted to it. And I think you know where that's going to go. All right, so we don't quite have the mechanism to explain how neutral matter can create a field, but we do know that force is equal to QE, so we can use this to go after an explanation. All right, so basically what this is implying is a neutral object makes a non-zero field. So we need to clarify exactly how this happens. And to do this, we need to go back to the structure of an atom. So we're going to do an easy atom, which is, of course, hydrogen. So 1 electron and 1 proton. So you've got your proton, and then you've got your electron. And if you recall, electrons don't have those nice, neat orbits. We have the electron cloud. Which is a bunch of probable locations. So the radius of the proton is approximately 1 × 10⁻15 meters, and the radius of the electron cloud is approximately 1 × 10⁻10 meters. That's what gets us our atom radius. Okay, so let's see what can happen to this cloud. In its natural state, it's going to be spherical. So it's got a nice spherical cloud. Could be different locations. So we've got our proton here, and then we've got our spherical electron cloud. Now, let's say that we took a positive charge and we moved it next to this cloud. So what's going to happen is the electrons, which are negatively charged, are going to be attracted to the positive charge, so they're going to move towards it. And then the positively charged nucleus is going to want to go in the other direction. So now we have something that looks like this. It's positive charge. So in this particular case, the electron cloud has shifted to the left. So it's more likely that the electron's going to be to the left than to the right. Now, just a quick note. If you bring this charge too close, it could break up the atom. Or become absorbed. So what we are talking about specifically is where it is close enough to shift the electron cloud, but not close enough to disturb the atom. And so what has happened is we've polarized the atom. So an atom is polarized if the electron cloud has shifted from an external charge. So conventionally, we draw polarized atoms like this, which is very, very exaggerated. This is really more accurate. And so essentially what this is a dipole. We have a positive and a negative charge of equal magnitude separated by some distance s. So you've made little dipoles of your neutral matter. Okay, so now that we know we've made a dipole, let's talk about different types of dipoles. So you have an induced dipole. This occurs when a neutral object is polarized by an applied electric field and it will go away when the field is removed. So when the tape in your lab was sticking to different things, you were inducing little dipoles that then went away when you moved the tape away. And then the permanent dipole these are two opposite charges separated by a fixed distance. So for example, a hydrochloride or an HCl molecule or H2O. So these are dipoles and these are nature's dipoles. So some things make dipoles easier than others, and this is related to their polarizability. And so the amount of polarization induced is related to the field that you apply. And this is measured experimentally. There isn't a good theoretical model to predict an object's polarizability. And I know this because I went through all of the equations when I was working on my dissertation to derive polarizability of different materials based on different properties, and you have to measure some of the constants experimentally. So polarizability P, the dipole moment is related to alpha, the polarizability, times the electric field. So alpha is the polarizability. This is what's experimentally measured. And it's materially dependent. And if you recall, P is also equal to Q times S. And the direction is from negative to positive. All right, so let's look at how this happens. So we can tell the story of the neutral atom and the point charge. So we know that the electric field of a dipole is proportional to 1 over r cubed, and we know that the electric force from a dipole is proportional also to 1 over r cubed. So let's walk through what would happen if we brought a neutral atom and a dipole together. So step 1, bring them together. So we have here a negative charge Q, and we have our neutral atom over here. They are separated by some distance r. All right, so this neutral atom is going to experience a field from this charge. So this is a negative charge, so the field is going to point towards the charge. If it was positive, it would be pointing the other direction. So the field from Q repels the electrons and attracts the nucleus. So step 2, we've polarized our neutral atom. So now the positive end is closer to our negative charge Q, and the minus end is further away. So we have plus Q2 and minus Q2. Q1 is still hanging out over here. And so we still have the electric field from Q1. And now we have the field from our atom, E2. The net field is going to be going in this direction, away from the positive charge, if we were to sum them together. And we would have the force on the atom and the force on Q1. So they are attracted to each other. All right, so once you induce the dipole, you get another field, and that field will then act on the charge that induced the dipole. Okay, so moving on. The atom has a dipole moment of P is equal to Q to S, and has E2 on the point charge. And so E2 is equal to 1 over 4 pi epsilon naught 2pr cubed. So this is the electric field of a dipole on axis. And this is equal to 1 over 4 pi epsilon naught 2 alpha E1 over r cubed. And for this, what we did is we substituted in P is equal to alpha E, and in this case it would be E1. All right, and we know E1 of a point charge. So E1 is equal to 1 over 4 pi epsilon naught Q1 over r squared. So we can plug that in to our E2 equation. So E2 is equal to 1 over 4 pi epsilon naught. To alpha over r cubed times 1 over 4 pi epsilon naught q1 over r squared. And so we can combine that all together, and we get 1 over 4 pi epsilon naught quantity squared to alpha q1 over r to the fifth. So the next step, now that we have the electric field, is to start going after the force. So what does that force on the point charge from the dipole? So F1 is equal to Q1 E2 is equal to Q1 1 over 4 pi epsilon naught quantity squared 2 alpha q1 over r to the fifth times r hat, and this is equal to 1 over 4 pi epsilon naught quantity squared 2 alpha q1 squared over r to the fifth times r hat. And what we can see is that the force on the point charge of a polarized atom will scale by a factor of 1 over r to the fifth. So when you induce an electric field by polarizing a neutral atom, it will then force on the charge, but it's a force that's going to diminish very quickly as you move further away from it. It's heavily distance dependent. So, and you can use reciprocity to look at the force on the dipole from the charge. So we would then know that F2 is equal to minus F1 is equal to minus 1 over 4 pi epsilon naught quantity squared 2 alpha q1 2 over r to the fifth times r hat. All right, so let's look at an example. We have a proton and a helium atom are at rest and 20 nanometers apart. The polarizability of helium is equal to 2.3 times 10 to the minus 41 coulomb meters per newtons per coulomb. So, what is the acceleration of the helium atom? All right, so the mass of the helium atom, so we know that the density is 4 times 10 to the minus 3 kilograms per mole, and there's 6.02 times 10 to the 23 atoms per mole, and so the mass of the helium atom is equal to 6.64 times 10 to the minus 27 kilograms. We know acceleration is equal to force divided by mass. So the force is 1 over 4 pi epsilon naught quantity squared 2 alpha q1 squared over mr to the fifth. So that's bringing in that mass right there. And so our acceleration is equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared, quantity squared. Make sure you keep track of all your squares into the fifths. 2 times 2.3 times 10 to the minus 41 Coulomb meters over newtons per coulomb times 1.6 times 10 to the minus 19 coulombs quantity squared divided by 6.64 times 10 to the minus 27 kilograms, 20 times 10 to the minus 9 meters, quantity taken to the power of 5, And we get that the acceleration is 4.5 times 10 to the 6 meters per second squared. So that is a pretty fast acceleration. So now what would happen to this acceleration if we were 100 nanometers from the proton? So a factor of 5. So since the force is proportional to 1 over r to the 5th, if you increase by a factor of 5, the force and the acceleration are reduced by 5 to the 5, which is 3,125. So the new acceleration is equal to 1,400 meters per second squared. All right, so let's look at so now that we know the basics of how polarization works, let's look at how it differs between insulators and conductors, starting with insulators. So, insulators are materials with tightly bound electrons. So charges don't like to move. So essentially, these atoms become polarized because electrons shift while staying bound to the nucleus. So if you get a positive charge here, these are going to stay in their atomic minus, plus. These are going to stay as atoms, and the electrons don't move more than approximately the radius of an atom, so 1 times 10 to the minus 10 meters. So you get the field because they polarize, but they're not really making that big of a shift. They're still staying together in their atomic structure when you polarize an insulator. So a few things to know about polarizing insulators. It happens very quickly. So you observed that the tape would become almost instantaneously attracted to everything. So charged particles will stay where they are. But there's no free electrons. And charges can be bound to a particular spot. All right, so now that we know about insulators, let's move on to conductors. So, conductors are where the electrons roam free. So here's the electron. It's very happy. It says, I can move more than 1 times 10 to the minus 10 meters. Yay! All right, so ionic solutions are conductors. And let's look at what happens when we apply a field to one of these solutions. So here it would be, you just have charges, they're all mixed up. So this is unpolarized. Now let's say we start to apply a field. So we have our field in orange. And what's going to happen is the positive charges will move in the direction of the field, and the negative charges want to move in the opposite direction of the field. So the liquid will start to polarize. And then eventually you will have this. All the positives on one and the negatives on the other. And then when you have that, then it's polarized. Now, to keep it polarized, you have to apply a constant field. Otherwise, it's just going to bop around and mix up again. So to keep a conductor polarized, you need a constant field. And this keeps the charges moving. And the speed of the electrons moving is called drift speed. And just to note, sometimes if you've got an ionic solution, you could have positive and negative charges. So drift speed could sometimes refer to moving charges more generally than just electrons. But typically we're talking about electrons. So drift speed is equal to, is written as a V with a bar over top, U times E net. V bar is the average drift speed. Of mobile charges, and U is the mobility of a charge. This is again materially dependent, so it's measured in meters per second over newtons per coulomb. And E net is the magnitude of the net electric field at the location of the mobile charges. And so note, if E is equal to 0, then V bar is equal to 0. And we can see that from the equation. So U is a material constant. It's not going to change. But if you don't have a field, then you don't have drift speed. And drift speed is required for polarization. Or sorry. Yeah. So let's go back to, our drift speed is required for moving charges. Let me rephrase. Let's go back to our ionic solution. So the applied field causes polarization. which induces a new field, the polarized field. So we've induced E polarization. And eventually, E net is going to be equal to E applied plus E polarization, which will be 0. Eventually, they're going to cancel each other out because they're in opposite directions. And in that case, then V bar is equal to 0. And the conductor is in equilibrium. And I misspoke earlier. You actually need the drift speed to be 0 to have it completely polarized. So V bar is in equilibrium. Okay. And so we can show conductors will reach equilibrium. We're going to do a little proof by contradiction. So 1, we're going to assume an equilibrium. E net is not 0 in ionic solution. 2, since E net is greater than 0, the force on the ions is not 0. Since U is greater than 0 and V bar is greater than 0, ions move in the direction of force. Since V bar is greater than 0, there is a net flow of charges. If charges are moving, it cannot be in equilibrium since, by definition, V bar is equal to 0 at equilibrium. And because we have reached a contradiction, we must conclude our assumption is wrong. E net is 0 in equilibrium. Right, and there you have it.